Good morning, I am Marco Manfredi and I work in the computer vision group of Professor Rita Cucchiara. And the title of my presentation is Gaussians of Local Descriptors for Image Understanding. First I will introduce the problem of image understanding, and then I will talk about local descriptors and how they are used in our proposal. I will present some experimental results and future work, and then I will finish with some research related to this field. Image understanding is a general term that comprises a lot of application. One of them is object recognition. That is, find which object is depicted in an image. For example, in that image, the object is an elephant. Another task is concept annotation. Concept annotation is a more difficult task because we don't know how many concepts there are in an image. For example, in this one we have sky, clouds, mountains, outdoor. Some of them are objects, some of them are more abstract like nobleur or other. And we will focus mainly on this second application. One of the most used dataset in object recognition is Pascal VOC 07, that is released in 2007. It contains about 10,000 images with 25,000 objects belonging to 20 categories. For example, there are airplanes, dogs, cars. The state-of-the-art solutions are able to obtain only a 65% of mean average precision, taking into account that a perfect solution would lead to a 100% mean average precision. So this problem is not already solved. All state-of-the-art solutions are based on local descriptors, and mainly on SIFT. SIFT means scale invariant feature transform, and they encode for this small squared image patch the gradient orientation and magnitude. For example, SIFTs are composed of 128 real numbers. There are some alternatives that are more recent, but we choose to use the SIFT descriptor because they give state-of-the-art performance and allows us to easily compare with other state-of-the-art solutions. Once we have extracted a lot of SIFT in an image, we have to find an image signature, a fixed length image feature, to be used, for example, in a classifier. How can we do this? Because we have to summarize the information coming from SIFT that can be a lot and can change from one image to other. A classic approach to summarize the SIFT information is the bag of words. The bag of words has been used for 10 years, and it learns first a distribution of SIFT over a training set. And then, given an unseen image, describe this image using the distribution that it learned from the training set. This approach now has low accuracy, so it's not completely state-of-the-art, but the major drawback is that to describe a new image, the description of a new image is strongly depends on the training set on which the initial distribution has been learned. Our proposal is a new image descriptor that is quite simple, and it is called Gaussian of local descriptors, named GOLD. And to summarize the information of SIFT inside an image, we compute their mean and covariance metrics. And this is our image description. For example, given this image, we can extract SIFT densely. That means that we extract SIFT in a regular grid, for example, one SIFT every 6 pixels. And given all this SIFT, we can compute mean and covariance metrics. We obtain a multivariate Gaussian of SIFT. I remember that each SIFT is 128 dimensional. And the final descriptor is the concatenation of the mean of the covariance matrix. So we have the mean that is 128 dimensional, and the covariance matrix that is 8,256 dimensional, because it is the covariance matrix is symmetric, so we have to take only half of it. The final image descriptor is 8,384 dimensional, so it's quite big. Now that we have an image description, so we can compute a fixed length image feature for every image, how can we find objects or concepts inside the unseen images? We have to learn them using a training set of labeled images. For example, if you want to learn the concept sun, we need several images of that depicts the concept sun. For example, hundreds of images. We can describe them using our descriptor and passes all this descriptor to a classifier. We choose to use a support vector machine. Support vector machine also need negative examples. So the positives are images that contain the sun concept. The negatives are images that do not contain the sun object. We tested our method in the ImageClef 2013 challenge in the scalable concept image annotation task. Task has 250,000 images for training that are taken from the web. 116 concepts. Some of them are objects like child, book, boat, car, bridge. And some other are more complicated and abstract, like cloudless, there's a sky without clouds, or close-up. Then we have 2,000 images for testing our solution. This task is very challenging because training images are not been manually labeled, but each training image as a list of words automatically extracted from the web page in which the image was found. This means that there's a lot of label noise. What does this mean? That in the training set, we have this image labeled as motorbike. Why? Because it has been found on a forum, or a motorbike forum, as a user avatar. So the system automatically labeled that image as motorbike, but this is clearly a big problem for us. These are the results. We are very proud of our method because we obtained the best mean average precision of the competition. To understand these numbers, the organizers have released some baseline methods. This is the simplest. So taking at random the concept, labeling the images with random concepts leads to a mean average precision of 8.7. The best baseline method that uses the bag-of-words approach gives 21.4. And our approach is able to reach 45.6 of mean average precision. There are some computational issues because the image descriptor is big, and each concept has an SVM that must be learned on all the 250,000 images. Although we use a parallel architecture, an IBM cluster, each run of our experiments takes about 10 hours of computation. And we have made, I think, 100 of runs to define the perfect solution. For future work, future work will include moving to large-scale problems. The biggest dataset available online is the ImageNet dataset that contains 15 million of images. But to do this, we need to reduce the dimensionality of our descriptor because it's unfeasible to compute 15 millions of descriptors and store them in RAM memory or also on disk. Because the disk space needed for the competition of image clef was of 200 gigabytes. So it's unfeasible to compute all these descriptors with the current dimensionality. Related research to this field is segmentation, because we want to use the gold descriptor in segmentation of related to cultural heritage in the DCHAT project, and use the same descriptor for superpixel segmentation, and this will be probably the work of next year. Okay, thank you.
Do you have an idea to reduce the dimension of your descriptor? Because this is the big issue.
There are a lot of possible solutions. The simplest one is PCA, the principal component analysis. But I think that there are better ways, and we have to test like 5 or 10 methods to reduce this dimensionality, and I don't really know which dimensionality can we reach. I think that reaching 1,000 dimensionality is our main goal. Yes, but PCA is the first method we will try. Yes.